Hi everyone. Can everyone hear me?
Yes.
Okay, let's start. Uh, let's go with the two homework problems I gave from the last time. Did anyone solve them? Here are the problems. So the first problem is Oracle models. I'll send the link in the chat. If anyone have solved this problem and have any idea, say it before we go ahead and solve it. Okay, no ideas? Okay, let's explain the problem very quickly. Basically, there are n numbers, um, and what the problem asks us to do, we have n integers. Okay, let's let's take any array here. Okay, we'll be given like n integers, and where's the problem? And the problem states that any arrangement is beautiful if it contains such numbers such that the indices, so like for example 1 and 2 is beautiful if the index of this number is multiple of the index of this number and this number is greater than this number. So more formally, so if I plus 2 and so on. Okay, so the problem states that an arrangement is beautiful if for every index in these numbers that we take. So for example, I plus 2 is a multiple of a of I, and also a of I plus 2 is greater than a of I. So for example, if I have um, this array here, so we could come up with a beautiful arrangement of 1 and 2. So 1 and 2 is beautiful arrangement. Why? Because the indices of them are 1 and 3. And 3 is a multiple of 1. And 2 is greater than 1. So that's okay. Okay? And also 1 and 2 and 3 and 6 and 9. This is a beautiful arrangement. And this is, I think, the biggest beautiful arrangement here because for every index here, it's a multiple of 1 because the first index is 1. I think no. This is not a beautiful arrangement. This is a beautiful arrangement. Okay. No, this is not a beautiful arrangement as well. Okay. This is a beautiful arrangement. Also, another beautiful arrangement is this is a 2, 3, 4, 5, 6. Is this 4? 2, 3, 4, 5. If you are to add something like 8 here, there will be another beautiful arrangement here because 4 is at index 2, right? And 8 is at index 6. So 6 is multiple of 2 and 8 is greater than 4. So this is a beautiful arrangement. So that we knew now what a beautiful arrangement is, we want to get the maximum size of a beautiful arrangement. So it's clear that for all these beautiful arrangements, they are of size 2. Okay, all of these are of size 2. But if we are to make another array here, like for example 1, 2, 3, 4, 7, 12, 8, 20, 2, 4. Hmm. 2, 2, 5, 6, 7, 8. We could get a beautiful arrangement here of size 3, which contains of 2 and 4 and 20. Because here the indices of these numbers, the first index is 2, and here the index is 4, and here the index is 8, right? So it's clear that 4 is multiple of 2, and 8 is multiple of 4, and for each of these integers, the next one is greater than the previous one. So 4 is greater than 2, 20 is greater than 4, and so on, okay? So here we could get a beautiful array of size 3, okay? Okay, let's solve it. Any idea how could we solve this? We are given n, and n integers, they are very large. Anyone have any idea before I start to code and explain the idea behind it? Okay. As you see the solution now, you will see that it's very easy, or it's easier than you think. Okay. Okay, let's explain how could we solve this.
So we can traverse to the indexes which are power of 2, right? Like 2, 4, 8. Those are in the power of 2, right? Like power
Yes.
of. So we can visit to those indexes which are power of 2, and while visiting also we can check like that particular element is greater than the previously visited element or not.
Yes. Um, mm, okay. Uh, that won't work with any beautiful array because you are stating that, for example, we check indices of 2, 4, 8, 16, and
Right.
32, right? And then check if the element here is greater than this, and here is greater than this, and so on, and take the greatest subarray, right? Or take all of this. But it could happen that we have an element here. Uh, what's this?
Correct.
Uh, it could happen that we have an element here, and here another element here that is smaller than this, but we have another element here that's greater than this and this. So we could end up with something like this, a beautiful. Okay, so this is at 16, and this is at 2, this is at 4. Okay, so we could end up here with a beautiful arrangement of size 3, which is 12, 10, and 3, or 12, 10, and 5. But you are saying that we'll check for every power on 2, um, and then check for every number if it's greater than the previous one only, right? But how to know that? So if you checked here with this greedy approach, we will end at 3, right?
Right.
Okay, so we want to have a dynamic a dynamic solution here that will work for any subsequence. Okay,
Yeah.
okay. We could do a simple DP here. Let's not call it DP first. It's an easy solution. Um, First, we'll solve the array from the last element. So it's clear that the answer for the last element is 1, right? Because there is no any element after it. So the size of the beautiful arrangement, the maximum size of a beautiful arrangement containing the last element is 1, which is this element, right? So we'll make here slots. So this is the array, and this is the answer. So what I'm saying here is that this is the array of numbers, and this is the array of answers to every index, okay? So if I said answer of 2, so this is one based index, okay? So this at the index 1, 2, 3, and so on. So if I said answer of 2 means the greatest beautiful arrangement that starts from 2, okay? Um, so if answer of 2 equals x, for example, so x is the greatest beautiful arrangement that starts from 2. So how to calculate answer for every index? It turns out that um, we could make it from the last element to the first element, and it will be convenient to get it. So the answer for the last element will be 1, right? That's it. That's the maximum thing. Um, what should be the answer for the second last element? So also the answer for the second last element should be 1, because the next multiple of this index, which is this index is 6, the next multiple is 12, but it's not here. So we'll also make it 1. Okay. And here the answer is 1. So eventually we'll make everything 1 at first until we find until we reach something like 3, for example. So here we are at index 3. So at index 3, we want to maximize this answer to make it as big as possible. So we will check the next multiple of 3, which is 6. So here 4, 5, 6. So the next multiple of 3 is 6, and it has an element greater than 3, right? So we will update this. So we'll update this with the answer of this element plus the answer of this element. Why? Because uh, if we found I, if we found such J, if J is divisible by I and R of J is greater than R of I, so let's make this more of a code style. So this is exactly what we'll do. We will check for every J that's a multiple of I. So it means that if J is divisible by I and R of J is greater than I, then we will update the answer of I with answer of J plus 1, right? So the 1 here means that we will take the ith element. So we'll take this element plus the answer of the jth element. So the answer of J could be 3, for example. And we know that if J is multiple of I, then for any multiple of J, it's also a multiple of I. So the answer of J will be valid for I, right? Because if R of J is greater than R of I, so the answer of J will be valid for I. So we'll add 1 to it and store it in answer of I. Okay, are you okay with this? Actually, this is the solution. But how we will perform it, we'll just go for every I and then go for its multiples. That's it. Any questions? Okay, I think this will be clear in the code. I'll take the input now and code it. First, sorry, take test cases.
Yeah, multiple in the sense the next to nearest multiple, right?
Sorry, your voice is echoing. Can you say this again?
Multiple, we have to check that multiple in the sense the next nearest multiple, right?
Yes, we'll go for all multiples, not the next nearest multiple. Okay, so here why the greedy approach fails. So we will not check for only the next multiple. So for 3, we'll not check only 6. We'll check 6, 9, and 12, and so on. Okay, because we could update it with the answer for 6, and then we find that the answer for 9 is greater than the answer for 6. Okay, so check for every multiple.
Okay.
Okay. Now we'll take n for the array. So we'll make 2 arrays here, one for the actual numbers and one for the answer. Okay. And one thing that we want to make the size of it n plus 1 because it will be 1 based indices. Okay. So we'll start from 1 and end at n. Okay. 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 So here, okay, first we'll take the array. Okay. We'll start from 1 actually. Now we want to calculate the answer for every element. And we said that we'll start from the last element and then come down. And for each element, we'll cross through its multiples. Okay, so we'll start from I equals to n, and then I greater than or equals 1, I minus minus. Okay. Here we will, okay, let's don't do that here. So here we'll make another loop that will cross through all multiples of I, right? So it's so similar that we have done to sieve. We're crossing through every multiples for such element. So for int j equals I plus I, is more than equals j plus equal I. So we're starting from the first multiple of I, which is I times 2, I plus I. And then until n, we're adding I at every j. Okay. We want first to initialize everything with 0. So in C++, making this, we'll initialize every element with 0. Okay. And here, just simple line of code will make answer of I equals max ans I or ans j. Okay. So here we are crossing. So I noticed that I didn't add 1. I will add 1 at the end. Okay. Ans of I plus equal 1, because I'll take this element and add it to the ans because it's starting with 0. So here I'm saying that the answer for I will be the maximum between all of the answers of its multiples. Okay.
Hi, the first loop I guess should start from n minus 1, right?
No, because you are saying that we'll forget about the last element.
No, in that loop I equals n, you're starting over there, and in the second loop j equals I plus 1, so it will overflow, right?
No,
I
it won't
plus 1, like,
overflow
now if I
because
n,
yes,
then j will be n plus 1, so the size of the array is n, right?
uh, yes, but it won't overflow because I'm here saying that j is more than or equals to n. So at the first time, j will be equals to I plus I, which is greater than n. But also I'm saying that j should be smaller than or equal to n, so it will break from the loop. Okay, so it will make sure every time that I won't go for any I that's greater than n, or any j that's greater than n. Okay, are you okay with this? Or there is something I didn't notice you are talking about? Okay, okay, I think this is okay. Okay, so I made, I created the answer for every element, but I want to take the maximum answer for all i's to print it because we want the greatest beautiful sequence. So make another integer called result, for example, to be equal to 0. And after I calculate the answer for every element, I maximize it with result. So result equal max result and so on. That's it. And then we'll print result. So the answer is actually calculated in this loop. Here where the answer is calculated. Okay. So let's take a small example here. Okay. We know that the answer for this array is 2. We'll trace the code and see what will be the answer for every element. So at first time, the answer for the last element will be 1 because I want to go through this loop and answer will be 1. Okay. And here also it will be 1 because there is no greater multiple. And for here for 3, I'll go through the first multiple of 2, which is 4, and then find that 6 is greater than 3. So this will be 1 plus 1, which is the answer for this, plus 1, which is 2. And for here, it will also, for 5, it will also be 2, because, for example, 6 is greater than 5, and the index for 6, which is 4, is multiple for 1, is multiple of 1, then this will be 2. So the answer for this will be 2, and our code will output correct. Okay, let's try this out. There's someone asking, please ping the question link here. I actually sent the question here in the chat. Okay. Okay. Let's put spaces to see what's happening here. So it's outputting 3, 3, 3, 1. Yes, yes, there is something I did check here. How is this? So I should check if R of j is actually greater than R of I. Okay, so for the problem, yes, it should be greater. Okay, so if R of j is greater than I, then I'll maximize the answer. Okay, here's it correct. Okay, do you all understand the code here and what's happening here? Yes, and there is another thing here. It's about the complexity. So n is large until up to 10 power 5. And you're seeing here that we are doing nested loop. So how would this pass? Actually, it's the same thing like C. We're doing nested loops, but it's so fast because the number of operations here is the first time for 1. For index 1, we'll go through this loop n times, exactly n times, because there are n multiples of 1, right? For 2, we'll go n over 2 times, because there are n over 2 multiples of 2. And then for 3, we'll go n over 3, and so on. So turns out that the number of operations is n plus n over 2 plus n over 3 plus n over 4 plus n over 5, and so on until 1, until n over n, which is equals to 1. Okay. So you might think that this is n squared or something, but actually this is n log n, and the proof for this it's proved on the internet, and it's we will not cover the proof now, but this we could take n as common factor, so it will be n times half plus third plus quarter plus fifth and so on until 1 over n, right? The times. So there is a proof for this here, for this formula here, that this equals exactly to log n. Okay, so from half plus quarter plus 1 over half plus third plus 1 over 4 plus 1 over 5 until 1 over n. Okay, so n times log n, it will be n log n, so this will be pretty fast. Okay. Okay, let's submit this. Okay, accepted. Let's move on to the next problem, which was homework also. So the problem says that find the number of integers I with the following property for every integer t such that identical j doesn't vary. Okay, so here for this problem, we are again given n integers, and we want to count the number of such i's such that they have no divisors in the array. Okay, so here what does this line means? So for every integer j such that j doesn't equals to I, a of I doesn't divide a of j. They doesn't have any number as a divisor in the array. Okay, so if I have something like this, 1, 2, 3, 5, 15, 10. Okay, so I want to count the number of integers here. Can you all hear me? My internet connection is lost. Can you all hear me now?
Yes.
Okay. So for one, and let's check for two. Also for two, it's okay. Three, which is one. Actually, I will not put one because one is a divisor for every number. Okay. So let's remove one here. So two is okay. Four is not okay because there is two and any divisor of five.
I have. I guess your voice is breaking a lot in between.
We are receiving in chunks.
It's audible to me, guys. Please check your connection.
Okay, okay, check this. Okay, 1 minute. Let's check this.
Am I just not audible? Are you speaking something or?
I think he's checking.
Can you all hear me now?
Yes, yes.
Okay. I think the connection will be okay now. Okay, let's continue. So as I said here, I'm counting the number of integers in the array such that they don't have any divisors in that array. Okay, so I said that 2 is okay because it doesn't have any divisors in this array. 3 is okay. 5 is okay because there isn't divisors. Note that I'm saying divisor, not multiple. Okay, so 15 is not okay because 5 is divisor of 15, but 5 is okay. Okay, here 2, 3, 5. 15 is not okay, and 10 is not okay because 10 have 2 as a divisor and have 5 as a divisor. So the answer for this array will be 3. Okay, 3 numbers. So that's it. We want to count these integers that satisfy this condition. Any ideas how to make this? I think this is easier than the last one. Uh, Here's it. Anyone has any ideas? Hmm. Okay, I'll give you 1 minute to think about it. And then tell me.
So here we should solve it in order of n, right?
We should what? I didn't hear correct. What did you say exactly?
We should solve this problem in order of n, right?
Yes, order of n or n log n, because n is up to 10 power 5, but shouldn't be more than n log n or n
Okay.
square root n. Okay, let me tell you how could you get this. So actually, it's very similar to the last one, and we'll use the same principle or the same rule we used in the last problem. which are crossing all the multiples for a number. So note that a of I is up to 10 power 6, right? So for any number in the array, we could pass through all of its multiples, right? And this will not be more than n log n. So for each number in the array, we could pass through all of its multiples and then eliminate all the multiples of a number. Because, for example, if I have 1, 4, 3, 2, 8, let's not take 1. Okay. So for 2, I know that 2 is okay because there is no divisors of 2. But let's make it in reverse. Let's eliminate all the not okay numbers, okay? So all numbers at first are okay. But first, we will check, for example, if we are standing at 2, we'll check all the multiples of 2, which are 4, 8, which are 4, 6, 8, and so on. And then we'll find that 4 is present in the array. So we'll eliminate 4, okay? So 4 is not okay. No, let's make it 0. 4 is not okay. And then 3 is not multiple, so it's okay. 8 is not okay. So now we eliminated 4 and 8. But then there are left 3 and 2, and they are not multiples of any numbers. So they will be okay. So the answer will be the size of n minus the not okay numbers. Okay. So how could we make this? We'll go to coding straightforward. First we'll take n, and then integers. Okay. So how to check for every multiple of numbers? First, we will not pass in the array as it is given to us. So we'll not first start with 24 and then 11. No, we'll pass through every numbers from 1 until 10 power 6. And then from every number from there, we'll check its multiples. If it's present in the array, then we'll make it not okay. And if not, then okay. Okay, so we'll make here an integer array called occurrence, and it will be of size 10 power 6. Let's make it constant. We'll make it +1 because it will be 0 in this index, and we want to check for 186 occurrences. Okay, so occurrences array means occurrences of x means the number of occurrences of x in the array. Okay, so if occurrences of x equals to 3, then this means that 3 appeared that x appeared 3 times in the array. Okay, so it will be easy to calculate this occurrences array. We'll just go through every number we have taken from the array and then add 1 to occurrences of that number. Okay, so actually we don't need to make an array a of n. We'll just take the numbers straightforward. Okay, so while n minus minus, and we don't care about what is n and what's the size of n. We'll take for every x, we will increase occurrences of x by 1. But first, let's don't forget to initialize this with 0, because first every element appeared 0 times. So here we calculated the occurrences array for each number, and then we want to make what we said here, make a loop that starts from 1 until 10 power 6, and then for every number, if it's present in the array, then go check all of its multiples. If any multiple is present in array, then just delete it or eliminate it. Okay. Okay. So let's make here. Okay. Okay. Answer of m means that number. Okay. Let's make this bool. Bool okay of n. This is more convenient. So bool okay of m means that if this number is okay or not. Okay. So at first we want to initialize all numbers as okay, and then eliminate the not okay numbers, right? So we'll name set okay as one, size of okay. So here every number at first is okay, and then after we go through the multiples of the numbers and eliminate that and eliminate them, we'll find the not okay numbers. So make the same thing that we did for the last time. From I equals 1 is more than equals to m I plus plus. So we'll see if occurrences of I, that means that if I appeared in the array, then I'll go check all of its multiples. For j equals I plus I, j plus equal I. Then I'll make occurrences of this number of j equals 0 because I am not interested of it at all now. So I'll make it 0, and then I'll make okay of j equals 0. So I could have done okay of j equals 0 only, but I also made occurrences of j equals 0 because I don't want to pass through this number again. Because if it's eliminated, then I don't want to pass through it again because any multiple of it will also be eliminated. Okay, so I won't pass through an eliminated number more than once. Okay, so here what's left is to count the number of ones in the OK array. Okay. But first there is something wrong here, is that there are extra ones, and these are the numbers that are not present in the array. Okay. What we'll do about them? What we'll do about them is there is an easier solution, is that we'll forget about OK, and then check for every occurrence if it's present. If for any x there is an occurrence of x after we have done this algorithm, if there is an occurrence of x, then sure I didn't eliminate it because I eliminate any occurrence of x that's a multiple of any other number. So if there is any occurrence of any number, then I'll add it to the answer. Okay. So here I'll make answer equals to 0. Then for the x for occurrences. So if x is not 0, of course, then ans plus plus. Okay, so that's it. So if there is, so x means an occurrence of some number. If there is an occurrence of some number, then I'll add 1 to the answer because this number is not eliminated. Okay, but there is still a corner case that we didn't check about it, and it is if we have duplicate numbers. So if we have 4, 4, 4, 4. So it's clear that for any 4 of them, it shouldn't be okay because 4 is a divisor of 4. 4 is a divisor of 4, right? But for this, we didn't calculate. We didn't make use of this corner case. We are checking only for multiples of a number. Okay, so if we have this, if we have something like this, all of these will be okay, right? So first we want to check if we want to add x to the answer, we want to check that x occurred 1 times only, because if x occurred more than once, then for sure it won't be okay, right? So just make for easier code. That's it. So answer plus equals x equals 1. So if x is is 0, then it's not it's eliminated or it's not in the array. And if x is 2 or more, then one of them is divisor of the other. Then I'll not add anything to the answer. Okay? And that's it. Okay, are you okay with this? Any questions? Anything you didn't understand? Okay, I think it's okay. Three. And here's the example we are talking about, which is 5, 5, 5, 5. If we didn't make this x equals equal to 1, then we would count 4. But here we only count the number of distinct or numbers that occurred once in the array. So here it outputs 0. Okay. Let's make this 5. Okay. Okay. Oh, I forgot to send you the submission for the last problem. I'll send it now. Okay. Okay, here is the submission to the first problem. And here is the submission for the second problem. Send them both in the chat. Let's go on to a new problem, which is most socially distanced subsequence. I'll give you 3 minutes to read this problem. I'll send in the chat and think about it and tell me if you have any ideas. I sent the problem in the chat here. Read it, okay? Okay, any ideas for this problem? Any ideas before I go to solve it? Okay, let's explain first. So here you are given n integers, and actually these integers are a permutation. And it means that they are only from 1 to n, and they are all distinct. So if n equals 5, for example, so we only have integers. So we only have these integers in the array from 1 to 5, and they are permuted in any order. So it could be something like 2, 3, 1, 5. Okay, so this is the array we are given, and we want to calculate the smallest subsequence possible. So the smallest subsequence, and of course it should be greater than 2, such that for any element in this subsequence, so let's make, so a of I minus a of I minus 1, yes, absolute value of this, let's make it more something from 2 minus a of 1 plus a of 3 minus a of 2 plus, and so on, until if the size of this subsequence is x, so let's call it k, then it will be until a of k minus 1. Okay, so we want to maximize this sum and minimize this size. Okay, so we want to get the maximum. So first we want to maximize the sum. So we want to get the maximum sum of a subsequence such that the second element minus the first element plus the third element minus the second element until the last element minus the second last element, of course with absolute value, is as large as possible. And then after we got this maximum sum, we want to get the minimum size. Okay, so let's take an example here. 1, 2, 3. No. If n equals to 6, then an example here is 2, 3, 4, 1, 6, 5. Okay, so let's think here about the maximum sum. So of course, the maximum sum, so a greedy approach here, and this will work. The maximum sum is actually taking every number, because if I took all the n numbers, then I'll have the biggest sum possible, right? Because I'll just have this and the second element minus the first element plus the third element minus the second element and so on. So I'll take this as it is, okay? And then the sum for this will be 1 plus 1 plus, let's make this more, 1 plus 1 plus 1 minus the absolute, so it will be 3 plus 6 minus 1, which is 5, plus 5 minus 6, which is 1. Okay, and this is equals to 10, 11. Okay, so the maximum sum is clear that it's so actually every element, but we want to minimize k, so we want to remove some elements from this subsequence such that the sum is still 11. Okay, so think about what elements to remove such that the sum will also still 11. Think about it a bit. It should be great to come up with. It's a good observation. So here k is equals to 6. We want to minimize k as possible until it reaches something like 2, for example. So from 2 to k. Any ideas? I want you to observe it by yourself. So okay, let's make a move here. So for example, if we moved 2, so we'll move 2. Okay. So if we move 2, so it's clear that the sum won't be 11. We'll remove this first one, right? So the sum will be 10. So 2 will not remove 2. But what if we remove 3? What will happen? So if we remove the 3, then I remove these two numbers, which is 3 minus 2. No, these two numbers, which is 3 minus 2 plus 4 minus 1. I remove them and add 4 minus 2, right? Because I remove 3, and then I'll add 4 minus 2, which is 2. So the sum is also 11. So now I decreased k by 5, right? But could I decrease it again? Let's see. So if I remove 2, then I'll remove this 2, and that's it. So 11 will be decreased by 2, so 2 we cannot remove it. And if I removed 4, I'll also remove this 2, because 4 minus 2 is 2. I'll also remove this 2, and then don't add anything else. So 11 will be decreased by 2. And if I removed 1, then I'll remove this 3, and then instead I'll be adding 2, because 6 minus 4 is 2. So also I decreased the number. So if we think a little bit for this arrangement, we'll see that actually it's optimal to not remove anything else. So the answer for this is k equals to 5. So it needs, yes. So the answer for this is these 5 elements. Okay. 4, 6, 5. So did you get any ideas how could we approach this? Okay, let's say the answer is straightforward. Let's take an easy array here with n equals to 4. Let's make it 6. So a very easy array should be 1, 2, 3, 4, 5, 6, 6. And if we take k equals to 6 at the first, so the sum will be 5, because here 1, 2, 3, 4, 5, right? So sum will be equals to 5. At k equals 6, sum equals to 5. So we want to decrease k, but without decreasing the sum. Okay. So first, we will observe that since this is a sorted array, so the last element minus the first element is the biggest sum we could reach. So the last element minus the first element is the biggest difference we could reach, right? So if we removed any element from the middle, it won't matter anything. So let's take, for example, a subarray of this, which is 3, 4, 5, 3, 4, 5. So 5 minus 3 is 2, right? And also if we took these 3 elements, it will be 4 minus 3, which is 1, plus 5 minus 4, which is 1. So it will also be 2. So if I have any sorted subarray, so it's optimal to take only the last one and the first one. Okay. So if I have 3, 4, 5, 4 doesn't make any difference, right? It will be 3, 5. Okay, because 4 just contributes with the same difference, which is 5 minus 3. So if I have any sorted thing like this, increasing or decreasing, okay? So 5, 4, 3, 2, 1. So from 9 up till 3, all these integers are sorted, so we'll remove all the middle integers, and this will be enough to get the maximum sum. And for this, we'll also remove all these middle, so this will be the same sum. So this observation got us to the answer that if we have any sorted subarray, we will remove all the middle elements and just leave the first and the last element. Okay, so for here n equals to 6, and for this array it will be k equals to and sum equals to 5. Okay, so let's take another. um, let's take this example. No, let's make another example. N equals to 6, 4, 5, 6, 1, 4, 3.
Hi, Ahmed, can you please hear me?
Yes, I hear you.
Yeah, okay. I understood the concept, whatever you're telling, but can you please clear the question once more time?
Sorry, what did you ask again?
I asked like if you can clear the question. What is actually question? So it will be better because I think I'm kind of a little bit confused in that.
Okay. Um, okay, so first, let's say the question again. We're given n, um, and we are given n elements, and the elements are only from 1 up till n. So the elements given as the array is from 1 up till n, and every element is included only once. So if n is equals to 10, for example, so I have all integers from 1 to 2, 3 until n, and they are all distinct. So I don't have any duplicates of 2 or any duplicates of 3 and so on. Okay. So if I'm given n equals to 6, so I'm given 6 elements, which are from 1 to 6, and every element occurs only once. Okay, so this is what the input is. I'm given n elements as a permutation. Okay, so what I'm asked to do is choose some subsequence of length k. So some subsequence, so we could take like 1 and 4 and 3 and 6. So this is any subsequence. Okay, and I want to calculate the sum of this thing. So what is this thing? So the sum of this thing is the second element from this subsequence minus the first element under absolute, so which is 3, plus the third element minus the second element, which is 1, plus the fourth element minus the third element, which is 3. So basically I'm taking any subsequence, and then I'm taking the alternating sum. So I'm taking the second minus first plus third minus second. So I'll have exactly n the size of this. So if it's k, so I'll have k minus 1 operations or k minus 1 additions to get this sum. Okay, so this sum is, for example, 6. So what the question asks us to do is to get the maximum sum possible. So the question asks us to get any subsequence and get the maximum sum possible, such that k is small as possible. Okay. So for example, if I took the whole subarray as subsequence, so a subsequence could be from size 2 to n. Okay. A subsequence in this problem could be from size 2 to n, because if I took size 1, which is one element, so I won't do any operations. So 1 minus what? Okay, so it will be 2 from 2 to n, and it's clear that the best sum would be at subsequence of size n. So this will be second minus first plus third minus second plus fourth minus third plus fifth minus fourth plus sixth minus fifth. Okay, so after getting this sum, we want to minimize k as possible. So here k is 6. So we want to minimize k as possible. Okay. So did you get the explanation for the question now?
Yeah. Thank you.
Okay. So and what we said here that the answer would be we will get to any sorted subarray. So this subarray is sorted. So 1, 2, 4, 5. This is sorted. And if we took the sum of 5 minus 1, it will be the same as the sum of 2 minus 1 plus 4 minus 2 plus 5 minus 4, right? Because it's the same thing. So if we imagine this as a segment here, so this is a segment at starting from 1, 1, 2, 3, 4, 5, 6, starting from 1 until 6. Okay. So this is a segment representing x-axis or something. Okay. And these are blocks. Okay. So the first block is of size 1. The second block is of size 2. The third block is of size no. The first block is of size 1. The second block is of size 1. So each block is of size 1. Okay. And this is the block number 1, and this is the block number 6. Okay. So if I took the sum of the first of these blocks from 6 minus 1, which is 5, to give us sum as 5, it will be the same as adding any number here. So if we get at the block number 3, and then we want to count the number of blocks, so we will get 6 minus 3 plus 3 minus 1, which is the same as 6 minus 1. So the number of blocks is also the same. So for any sorted subarray, let's think of it as a segment, and we are just counting the number of blocks from 1 up till 5. So it will be the same if we just said 5 minus 1, and as we said 5 minus 4 plus 4 minus 2 plus 2 minus 1. It will be the same number of blocks. Okay. So the answer would be okay. The answer would be we'll get to any sorted subarray, increasing or decreasing. Okay, so if we have something like 7, 10, 8, 7. Okay, so for this sorted subarray, we'll remove 4 and 2. It won't make any difference. And 3 and 6 and 10 is also a sorted subarray, so we'll remove 6. And 10 and 8 and 7 is also a sorted subarray, so we'll remove 8. So here we got to the maximum sum with the minimum k. So here initially n was equals to 10 because we had 10 numbers. And here we got the maximum sum with k equals to 5 only. Okay, so here how could we solve this problem? Let's jump to the code. We'll take t. And then we'll take n integers. Let's make first. Okay, actually we could make an easier loop here, which is index. So here we are passing through every element in the array, and just take it. Okay. So now we want to remove every adjacent element that they are in a sorted subarray. So 1, 2, 3, 4, 5. So we will have so the output should be the subsequent that we got. Okay, so here for this example 3, 2, 1, we should output only 3, 1, and we remove 2. Okay, so we should take the first element and the last element in a sorted subarray. So how could we do this? We'll make a vector here, which is empty, and then we will add to it the elements as we pass through the array, okay? But how are we adding these elements? First, it's obvious that the first element should be added, right? Because the first element in any permutation will be in some sorted subarray or not sorted subarray, and it won't be removed. So the first element and the last element will be added to the vector. So v to push back r of 0. Okay, and then after that first element, so imagine we added 1. So after that first element, we'll make a loop starting from the second element, and then check if there is an element larger than this after me, then I won't add this element. Okay, so if the first element is smaller than me and the third element is greater than me, then I won't add this. But if I am at something like this 1 3 1 3 2, then I added the first element, and then the second element I will look at the next element which is smaller than me, and the first element is also smaller than me. So this is not in a sorted subarray. So I will add it, okay? And then the last element for sure will be added. So I'll make a loop here. And it will be starting from 1 because I added the first element is smaller than n-1. So I'll go up till n-1 because I'll also add the last element after this loop, okay? So after this loop, I'll add the last element because the first and the last will be always added. So here I will check if I is greater than the previous one and also greater than the next one, then I'll add it. If not, then I won't add it, okay? So I'll make this if r of I greater than r of I minus 1. Equal r greater than r of I plus 1. So it may seem a bit confusing here, but it's easier. So let's look at this condition. So I'm saying that if r of I is greater than, so if this element is greater than the previous element, and this returns a bool, right? And if this bool equals to this element greater than the next element, so if I have something like, as I said, 1 2 3, so 2 greater than 1 will return 1 here, right? And 2 greater than 3 will return 0 here. So this will not be equal, okay? So I'm just saying that if this element is greater than both of the elements at the left at the right, then add it. And if it's smaller than both of them, then add it. But if not, if there is an element greater and an element smaller, then I won't add it, because if it's something like 1 2 3 or 3 2 1, so it won't be greater than both or smaller than both, right? So I will not add it. So I'll just add it if it's greater than both or smaller than both. That's it. And then I'll do the output here, the size of the vector. So that's it. Any questions about this approach? If you have any question, ask. If something is not clear. Okay. So here it works. Let's submit. Okay, accepted. Here's the submission link. Okay, let's move on to the next problem. Here's the problem. I sent it in the chat. Read it for 3 minutes and think about how to solve it. Okay, so the problem says that we have a monster of health H and we'll be given an n spells, and each spell consists of hmm, each spell decreases the monster. So if we are to use the ith spell, then it decreases the monster by Okay, so we're given n spells, and each spell decreases the monster's health by A and adds and with the cost of B. And we want to use spells as we want, such that the cost of them is small as possible and the monster's health is more than or equals to 0. Okay, let's take an example here. So the monster's health is 9, and I'm given 3 spells. Let's move this 3, which is 8, 3, 4, 2, 2, 1. So I want to get the minimum cost. So the costs are 3, 2, 1. To decrease this 9 to make it smaller than or equals to 0. Okay. I could take this spell and it will make the monster's health 1 at cost 3, right? And then take any other spell. But the cost will be greater than or equals to 4 here. So if I took the first spell, so spell number 1, it will make h equals to 1, right? Because it will do 9 minus 8, and then with cost of 3. So then I'll have to make another, I'll have to use another spell, which is, for example, I could use this spell, spell number 3, which will make h equals to -1, because I'll make 1 minus 2. So the monster is dead now, at cost equals to 1. So here the total cost equals to 4. And is this minimum? Yes, 4 is the minimum cost we could get out of these spells, and we could use any spell more than once. So if we used these last 2 spells instead of this first spell, so if we used the second spell and the third spell, let's use second. It's noted by 2, 3, and the sum of decreasing the h will be 6, and then we'll have to use another spell, which is, for example, 2. So we'll use 2, 3, 2, and this will make 9 minus 4 minus 4, 9 minus 2 minus 4 minus 4. Okay, and this will be -1 also, but this is at cost 5, right? Cost equal 5. So this is not optimal. Okay, so it's clear now that we want to make the monster's health smaller than or equals to 0 with the smallest cost possible. Any ideas how could we do that? So we have multiple choice. At each spell we could use multiple times. So we could use 2, 2, 2, 2, 2. Okay, so 2, 4 times. But this will cost us, this will not be enough. We could use not 2, 3, sorry, 3, 3, 3, 5 times. So I could use the third spell 5 times, and this will be, and the monster's health will be 9 minus 2 times 5, which is -1, and at cost of 5, 1 times 5, at cost of 5. So I could use any spell more than once. Any ideas? Think of it 1 minute, and eventually you'll have a good idea. Okay, let's explain the solution to this problem. So let's consider the constraints here because these are very helpful. The health of the monster is up to 10 power 4, and the number of spells is up to 10 power 3. Okay, and the cost is up to 10 power 4, and A is up to 10 power 4. So we could use an O of n squared approach in this problem because n is too small and h is too small. So we could use n times h or n squared or even h squared. So all of these complexities will work. Okay. This will let us think in a DP solution. So a DP solution will involve that if we have some h, so we will check all the spells from 1 to n. Check all spells from 1 to n. We'll check all spells from 1 to n, and then decrease h by a of this spell by the power of this spell, and then add the cost, and then check for every other h. So for dp of some h, it will be equals to minimum. Let's make a pseudocode here. So dp of h will be equals to for I from 1 to n. So dp of h will be equals to minimum of either dp of h minus a of I plus the cost of this spell plus cost of I, or yes, this will be the answer. So dp of h will be equals to the minimum for each I. We will minimize. So let's make it more coding style just to make it more clear. So dp of h equals minimum between dp of h or dp of h minus a of I plus cost of I. So we will the answer will be the minimum of taking this spell or not taking it at all. So if we took this spell, so the answer will be dp of h minus a of I because we'll increase h and then we'll add the cost. And if we didn't take it, then it will be just dp of h. This could be confusing now, but it will be easier with the top-down approach here. So we'll make it a recursion DP. It will be very easy to understand now. Let's make the function straightforward. We'll make a function called solve. And here it has h. H denoting the current health of the monster. Okay, so the base case for this function is if h is smaller than or equals to 0, then return 0. Okay, so if it's, let's make it smaller than 1, the same thing. If h is smaller than 1, then the monster is dead, then I'll return a cost of 0. Then I won't use any other spell. Okay, otherwise, the answer for this will be, let's int result. We'll make it something very big, like 29, because we will minimize it as we go on to check for all the spells. Okay, so let's have here an array noting the values. So int a of const n equals 23. So n is up to 10 power 3. So here noting the value of A and the cost, let's make this V, which is val, and this cost, to make the names more clear. So this is the value of the ith spell, and this is the cost of the ith spell. Okay. So I want to minimize the answer, so I will go through all the spells. Int I equals 0 is more than n I plus plus. So result will be the minimum of trying all of these spells. Of course, I have n here. So result will be minimum of either result or solve h minus val of I plus cost of I. So what I did here is I passed through all the spells and then checked. If I solved this spell, then if I took this spell, then I'll solve of h minus value of I. So I'll go to solve h minus the value of this spell, and then I'll add the cost, right? And I'll take the minimum of all of these and then make it to the result. So result at the end, of course, won't be equals to 2e9. It will be minimized as small as possible. So now I'll return result. Okay. But this is a recursion. It will go in exponential time. It's not dp. So we'll make a memoization here, memo array. And h is up to 10 power 4, right? So it will be on 2, 3, 4. This is 4 zeros, right? 1, 2, 3, 4. Okay, so I'll make here int result equal mem of h, and if result equals -1. So if I didn't reach this state before, this h before, then I'll just calculate it. And if I reached it, and if it's not -1, then I'll return it. Okay, that's it. Result equals 29. So let's take the input. First, we'll take some h. And n is up here. And then we'll take the values for a and b. Send verify cost of I. But first, let's not forget to fill the memo array with -1s. Size of memo. And then we'll print solve of h. So h is full at first, and then we'll solve h. And every time we'll decrease it and take the minimum spell for each time. Okay, and then we'll return the minimum cost possible. But there is something here. Minimum. Okay, let's try this. Yes, there is a bracket mistake here. So I'll solve h minus value of I, and then add cost of I. Okay. Okay, any question regarding this DP? Yes, ask if you have any questions. Okay, no questions. Okay, let's submit this. Okay, here is the submission link. Let's go to, I think, the final problem today. I sent the link in the chat. Read it carefully. Take 3 minutes and think about the solution. Okay, let's explain the problem. You are given n, and n is up to 10 power 12, and then you choose any integer z satisfying these conditions. So z is a divisor of n, and z is a prime raised to the power. So actually z is a prime multiplied, is a prime power something. So here we are given n, and then I'll choose some z. And what does this means? That z is some prime par x. That's it. Okay. So z is p par x. X is from 1 up to anything. So z should be some prime multiplied by itself again and again. And z is a divisor of n. So z is divisor of n, and z is some prime power something. And also, if you choose some z the first time, I cannot choose it at any other time. So let's take an example here. We have n equals to 24. If n equals 24, then let's because we are only choosing prime powers, so let's make the prime factorization for this number. So it will be 2 times 2, 12 over 2, 6 times 2 times 3 times 3. Okay. Okay, 6 times 2, 12 times 2, 24. Okay, so this is 24. 24 equals 2 power 3 times 3. So the goal is we should find the maximum number of times we can choose z to be applied. Okay. Yes, and I forget, every time we choose z, we divide n by z. So if at the first time we choose z equals to 2, for example. So at first operation, we choose z equals to 2, and 2 is prime, and we'll choose z equals to 2 power 1. Okay. So we'll make 24 over equals to 2, which is 12, and this is one operation. So the second time, for the second operation, we cannot choose 2 because or we cannot choose 2 power 1 because 2 power 1 is chosen before, right? But we can choose z equals to 2 power 2, for example, because it's not chosen before. And then we make 12, which is the new number. 12 over equals to 2 power 2, which is 4. And then this will be equals to 3, right? So the second operation, we could choose the only number that's left, which is 3. Okay, so we can choose z equals to 3 power 1, and then make 3 over equals to 3, which is 1. And that's it. You cannot do a fourth operation because we have only left with 1, and there are no prime divisors of 1. Okay, so for 24, the answer should be 3, and this is the optimal way. Okay. Because we want the maximum number of times the operation can be applied. If you choose the first time, z equals to 2 power 3, for example, then at the second operation, then here z over equals 2 power 3 will be equals to 3. Then at the second operation, we'll be left with only z equals to 3. So these are 2 operations. Okay. So 2 operations is not optimal. So we want to make the maximum number of operations possible. For this 24, it will be 3. Any ideas how could we do this? We solved prime factorization problems multiple times before, so we should be comfortable with prime things here. Think a little bit how to maximize the number of operations we can apply. Okay, let's see the idea here. So the idea here is we'll get the prime factorization of n, and let's p denotes a prime number, okay? So the prime factorization will be some p1 power a1 times p2 power a2 times p3 power a3, and so on, okay? So we'll get the prime factorization of n, and we know how to get the prime factorization in square root time, because n is up to 10 power 12, so square root 10 power 12 is 10 power 6, and this is enough, okay? So n will be equals to some prime power some number times some prime power some number times another prime power some number. So the optimal approach here is, so if we took some prime one time, so if we took p1 power 1, we cannot take p1 power 1 again. We can take p1 power 1, then p1 power 2, then p1 power 5, for example. So the optimal thing here is to take p1 power 1 at one operation, then p1 power 2, then p1 power 3, and so on until there is no p left in n, okay? And then take p2 power 1, then p2 power 3, power 2, and so on until the last prime number will take power of 1, then power of 2, then power of 3, until they are done, okay? Let's leave this here. So first we will make prime factorization for n, okay? And we will count the number of powers of each prime. Okay, so let's take the input here to be long sin n, and we want to have an array that represents the powers of each prime number, okay? Each prime could be very large, so we cannot make this array, we will make it a map, okay? Because the size cannot be up to 10 power 12. So we'll make this map that maps from long to integers. Powers. So if I call powers of 5, for example, so powers of 5 will be equals to the powers of 5, which are the powers of 5 in the prime factorization of n, okay? So I prime factorize n and then complete this power map. So let's do the prime factorization for n. So as I explained the prime factorization method last time, we will go from 2, print I equals 2, and then I times I, actually this will be long. I times I is more than or equals to n I plus plus, okay? So if n mod I equals to 0, then I've found some prime which is divisible by n. Then I'll make this while n mod I equals to 0, then n over equals to I, and then powers of I plus plus. So what I've done here is I eliminated this prime factor from n, and then added 1 to the powers of this prime. Okay, that's it. I don't have to do this. Okay, if n not equals to 0. I don't have to do this if also not equals to 0. Okay, so after I finish this loop, I'll have powers that represents the number of powers for each prime in the prime factorization of n. But I could, like I said, I could have left with n greater than 1, and if n is greater than 1 after this operation, then for sure n is prime. Then if n greater than 1, then powers of n plus that. Okay, so now I calculated the powers for each prime number, and then I want to calculate the actual answer. I have here int answer equals to 0. Then, so as I said, I want to go from 1, and then I want to take z equals to p power 1, then p power 2, then p power 3, and so on. So I will loop through every prime in this map, okay? And then I'll decrease the powers for each prime, as I said here, 1, 2, 3, 4, and so on. So to access every element in map, I'll just make for each loop here, for O2x powers. Let's make this p. So for O2p powers, this O2 is actually a pair of long and integer. Okay, so p dot first is equals to the actual prime number, and p dot second is equal to the power of this prime number. Okay. Let's make this x, and p is the prime number equals x dot first, and this is long of course, and int power equals x dot second. Okay, so now I want to I know now that p power power is some prime in the prime factorization of n, and I want to decrease power until it reaches to 0, and in this manner 1, 2, 3, and so on. So I'll make a for loop starting from 1 equals 1, and then I'll make I++, and I'll tell you the base case now. Okay, so I equals 1, and then I++, and then I'll decrease power. First I'll decrease 1, then I'll decrease 2, and then I'll decrease 3, and add to the answer. Okay, so the base case should be power is greater than 0. Okay, so whenever power is greater than 0, then continue. If not, then don't continue. Okay. Actually, no, it should be power minus I greater than 0. Okay. So if power equals to 1, then the first time power minus 1 will pass, and then okay. And if power equals to 3, then the first time power minus 1 equals to 2, and then to pass. The second time I will be equal to 2, and then power minus 2 will be okay, and then will pass until I've reached 3, and then power minus 3 is not okay. Okay, so now we'll make power minus equals to I, and then just answer plus plus. So I'll decrease this integer the first time by 1, then by 2, then by 3, and then add to the answer, because I chosen this as z, something. Okay, and then at the end just see out answer. Is everything clear here? I think I explained this fast, so if you have any question regarding any point, ask. Okay. Let's try this. Actually, I don't need to store this p. Okay. Let's try. Okay, 3. 1 0 64 3 1. Okay. You sure all you understood this algorithm? This solution? Okay, let's submit. Okay. Here's the link to the code. Okay, we're finished today. And I'll give you one homework problem. And I hope you solve it by yourself and submitting it, writing the code for it. Don't wait until I solve it, because you won't be better unless you solve the problems by yourself. Okay? Um, Here's the link to the homework problem. Okay, any questions for today before I leave? Okay, I think no questions. Okay, see you the next time. Bye.